Hey, hello, students. This is Bob Jackson. We're here with Investigative Science, the SE 201 class here at St. Mary of the Woods College. This is chapter 4 and it is on heat and temperature. Heat and temperature, pretty good, pretty important concepts to learn. Actually, they play a factor in all of our lives. Okay, heat and temperature. Drive things, okay, and make things comfortable or make things uncomfortable. Okay, we heating and cooling is a big industry, and I imagine if you talk in your classes that someone's mom or dad or somebody works in heating and cooling, HVAC, they'll call it. So you can kind of talk that to your students that talking about heat and temperature in these units in a science book is one thing, but dealing with it in real life is important because when the power goes out and your air conditioner don't work and things like that, heating and cooling become extremely important. And then wintertime, when it's really cold outside and the power goes out and you no longer can have heat in your house, it becomes a huge deal. So heating and cooling, heat and temperature are, like I say, important concepts to talk and to teach students about and give them some base knowledge of it. Okay, so this unit, like I say, it's on heat and temperature, but the main concepts we're going to get into talking is kinetic energy, very little about kinetic molecular theory. Then we're going to talk the phases or states of matter and phase changes, which I think is extremely important for elementary kids to start learning about. And they can learn states of matter down first, second, third grade pretty easy, and actually understand what they are. Okay, and they can experience them every day. Okay, we're going to talk about temperature, how we measure temperature, the tools we use to measure temperature, and the units that we use to measure temperature. Okay, then we're going to talk some about heat transfer, way heat transfers from one body to another or transfers through the atmosphere or through the air in this room or through objects like this is a coffee cup, which it's a igloo thermos style one to keep heat in. Okay, we have those for a reason. Whereas I've got this is one that I try to keep my stuff cold. It's a water bottle, fancy water bottle, but it'll stay cold all day long because of what it is. And I am keeping the heat out of this one. I'm trying to keep the heat in this one, and that's what we want to kind of teach the kiddos. So we're going to talk about some key terms then in the movement of heat, and that's going to be conduction, convection, and actually radiation. Okay. Then we're going to start here. This is kinetic energy. Yeah, you can't start talking about heat and temperature and those terms without talking kinetic energy. Okay. Um, Previous to this chapter, you should have already, or previous to talking this content, should have already introduced these terms to students, what kinetic energy is and what potential energy is. Of course, potential energy is stored energy, and then kinetic energy, energy of motion. Okay, and we don't have to talk too much on potential energy in this unit because heat and temperature is all about kinetic energy. Okay, energy of motion. And this energy is what makes heat. Okay, so what I'd like to start out with on this is go to this PET simulation. Okay, in which we'll go to the online site. And I'd like for you to get your students on this site, get them playing around. This is Energy Skate Park, and it's a fun way to teach some stuff about kinetic energy and get kids to understand kinetic energy. And actually, it's convert from kinetic to potential and potential back to kinetic. So this Energy Skate Park here, I want to show you the things to do with your kids on it just a little bit, and then just let them play around some more than anything else. Okay, first of all, you'd want to drop this down and try to get them to see and understand what kinetic and potential energy are. And remember, we're mainly trying to get them to see kinetic energy right now, and that's why we're at the Energy Skate Park. Okay, you can add a grid in here. Okay, so they can actually put a measure to the movement of their skateboarder. Okay, and then reference height, it's okay, but I don't know that you need it for the elementary levels. You could do it. Okay, you have a pie chart, which will put, when you put your person up here, it puts a pie chart on top of their head. Okay, see the pie chart? Okay, that's where it's showing the conversions of the kinetic and potential energy. Green is kinetic and potential is blue, and you see those changes in movement. That's what you kind of show students. But you can also see it right over here. So whether you use a pie chart or not, I don't know, it doesn't make a difference. Since you've already been through a unit and taught students, or hopefully by this point you've taught students about speed, so you can look at the speed and relative to kinetic energy, okay? Okay, this is speed in meters per second, okay? And then this is where you can change the track, but the easiest way to change the track, get them play around, is put their track on here, okay, and go to these different ones, okay, and play with their skateboarder, okay. But anyway, when you put your skateboarder up here, then you see where you're going to get the greatest potential energy up here, and that's where when you put it up here, you can see the potential energy over here. All right, as the skateboarder's going down, increasing kinetic, the potential energy goes down as kinetic goes up, and vice versa. Okay, now the person will keep going, but eventually they're going to slow down as they lose more and more kinetic energy and energy as they lose energy of motion. Okay, now the other things you can do on here, you can increase the friction on the track, which is going to slow them down quicker. Okay, you can add more gravity in, which is like, that's going to see, watch the changeover real quick. Okay, and then you can change your person, the mass of the person, and see what that does relative to their overall movement. Okay, then like if you go to this track, you can take her and put her up here, put her on there, she goes, and she stand on the track, because stick to the track's on. If I take stick to the track off, then you propose to the kids, well, what's she gonna do? Well, there she goes. Okay, you can even, on some of the other track settings, you can send her right off the track. Okay, but if you want her to stick to the track, then she won't go off the track. Okay, so but you can leave that off, and they can when they change the track, they can get it. If this side over here is lower than this side, they'll throw her right off the track. Okay, and so this is pretty neat. You can talk about, if she doesn't have enough kinetic energy when she goes over this, what happens? You can make that happen. Okay, she'll go there and not make it. She goes back down. Okay, if she runs out, if you get her just right, she'd fall off of it. Okay, but it's kinetic energy. Okay, the other thing you can do is bring the tape measure here. You can measure the sections of the track. Get them doing some measuring. Okay, how high that hill is. Okay, how high the one is over on the other side and so forth. Okay, so it's just an activity that you can do with your kiddos. Okay, okay, that's that one. Then you have this one. Okay, this is, I like this, that it shows straight out kinetic energy. Okay, the motion of these balls or dots or whatever, that's kinetic energy. Now in this one, you can change the kinetic energy by doing this. A whole lot of kinetic energy, less kinetic energy. Whole lot of kinetic energy, less. Okay, you can change the molecular count in there. So you can see fewer, a lot less collisions, and the overall kinetics is less dynamic, more dynamic. Okay, you can throw some heat in by turning the heater on. Of course, as the temperature goes up, then that's why we're talking kinetic energy and temperature. Then you get a whole lot more kinetic energy going on as the heater's hotter. Okay, you can put some gravity in there, increase the gravity down there, and you should see more collisions down here at the bottom. The gravity's pulling more down this way and less up here. Okay, so that's kinetic energy and ways to show it to the kids. And there's other things that you can look at online that that are good. Okay, so now then, that's kinetic energy. That's an introduction to kinetic energy. Let's get them to see what kinetic energy is. So let's go to temperature. Temperature is a measure of the average kinetic energy within matter. So that's the reason we talk kinetic energy. Okay, the measure of the average kinetic energy in something. Okay, is temperature. Everything has a temperature. Okay, the only thing that doesn't have a temperature would be at absolute zero, and I don't know anything in common life you're going to find at absolute zero temperature. Okay, so temperature tools. What are the main tools for working with temperature? Thermometers. Okay, so there's some common thermometers from the very basic to one that we put outdoors. This is a meat thermometer. It's got a metal pointer on it, so when we put that metal pointer down in the meat, we're only getting the temperature inside the meat. Okay, and then these come real popular during the pandemic where they're touchless thermometers. Rather than sticking the thermometer in their mouth or wherever else on their body to get a temperature, they can just hold it up there towards your forehead or whatever. Okay, and get a temperature. But you can also get temperatures of hot pans and different things like that around the house if you just want to play around. Have kids, if you bring one in the room, you can take temperatures of some surfaces in the room with them. Okay, and temperatures of the kids around the room. Okay, but thermometers. The other thing to talk about is what's in the thermometers. Like here, this is that's an alcohol thermometer. It's a dyed, but as it heats up, this just simply expands up the tube. When things get hot, they expand. So this is expanding up the tube, and then we have a scale for it to measure. Okay, behind these, and these would be a good thing to do is tear these apart and show kids. Back inside them, there's going to be a bimetal. It's made up of at least two metals, but it's a spring wound up in there. It may look like copper, and then copper's got something else put in there with it, but it will expand as it heats up. The spring will expand outward, and that's what turns that needle around. On actually both of these, this one and this one. Okay, they'll have, if you tear them apart, there will be a coiled up spring inside them that as it heats up, it expands. Okay, those are thermometers, and it'd be kind of neat to teach them how they work. Okay, so here we're looking at thermometers again, but we're looking at the temperature scales. We have 3 temperature scales that we work with: Fahrenheit, Celsius, and Kelvin. Okay, and they're all 3 important to teach in science in K through 12. Maybe at the lowest grades, just teach this and this. By 4th, 5th grade, you can teach Kelvin. Okay, it's a real easy scale. It's actually the easiest one. Okay, so if you take the Fahrenheit scale or talk Fahrenheit, if you're going to take a Celsius temperature and convert it to Fahrenheit, you're going to use this formula: 9/5 degrees Celsius plus 32. 9 divided by 5 is 1.8. So some people know this number is 1.8. That's what I always actually did. But your textbooks always give it like this. So you're going to take 9/5 times the Celsius temperature, or take 1.8 times the Celsius temperature and add 32. That'd give you a Fahrenheit temperature. Celsius, if you want to go to Celsius from Fahrenheit, you're going to use this formula, where you're going to take the Fahrenheit temperature minus 32 times 5/9. So if you'll notice, this is just opposite of this because we're doing the conversion in the opposite direction. Okay, so anyways, it's pretty easy conversion. You just take your Fahrenheit temperature, subtract 32 off of it, get that answer, and then take it times 5 divided by 9. Okay, and then Kelvin is actually the easiest one of all, and we'll always just do Celsius to Kelvin conversions. You just add 273 to the Celsius temperature, and you'll be on a Kelvin scale. Kelvin scale was made so you have no negative values on them. In some areas of science, we can't deal with the negative numbers on the temperature scale and do the math. Okay, so the Kelvin scale was developed for that. And the other unique thing is with the Kelvin scale, at 0 on a Kelvin, it is absolute 0. You can't get any colder than that. Whereas on the Celsius and Fahrenheit, you'll notice you have temperatures down way below zero. Okay, like on the Fahrenheit scale, absolute zero would be negative 459.67 degrees Fahrenheit. Okay, it's negative 273.15 degrees Celsius, absolute zero. Okay, so that's where we can have some cold temperatures like up in Alaska and up in Canada and so forth in winter, international falls, US, that you can get negative 30 degrees Fahrenheit. So you can get a lot of negative temperatures. But there are areas of science that we can't deal with negative negative values in the math because it just won't make the math work right. So we use the Kelvin scale. Okay, so some key things to point out with kids on these is they ought to know the boiling somewhere in elementary school. I'll just start knowing the boiling point of water. Okay, the temperature of water boils. That's 100 degrees Celsius, or it's 212 Fahrenheit. Okay, on the Kelvin scale, water boils at 373.15 Kelvin, and we don't say degrees on Kelvin. Okay, because it's not a degree scale. Okay, body temperature, our body temperatures are right at 98.6 Fahrenheit. Okay, give or take some. All of us don't have exactly by any means. On Celsius, that's right at 37 degrees Celsius. But our body temperatures are around 310 Kelvin. Okay, so it takes getting used to. And it's kind of impressive to say my body temperature is 310 K. It is. Okay, or it should be close to it if you're a normal functioning human being. Okay, and then you ought to know freezing. What temperature does water typically freeze at? 32 degrees Fahrenheit, 0 degrees Celsius. But water also freezes at 273.15 K. Okay, Kelvin. Okay, so it's good stuff to teach kids and show them. Okay, here we're going to do some temperature conversions, and we're going to go from Fahrenheit to Celsius, Celsius to Fahrenheit, and then go to Kelvin. And I'll have you do some problems for that, and that'll be the extent of our problems on these units, because the rest of it gets into thermodynamics and thermochemistry, which is well beyond elementary school. Okay, so if we're going to go from Celsius to Fahrenheit, this is an example here. We're going to convert 350 to Celsius. We're going to take that 350, subtract 32, take it times 5 divided by 9. Take it times 5 nines. And there's your answer. If we're going to go the other way, go from Celsius to Fahrenheit, we're going to do this. We have 25 degrees Celsius, and we take it to Fahrenheit. This is what we do. We take the 9/5, which is 1.8, times 25, then we add 32, and that'll be 77 degrees Fahrenheit. So if it's 25 degrees Celsius outside, it's 77 degrees Fahrenheit. Okay, and then we'll go to Kelvin. Kelvin's the easiest one of all because all you do is add 273 to the Celsius number. So that's it right there. So 22 degrees Celsius plus 273 is 295 K. Okay, pretty easy math. Okay, that can be done at the elementary level, no problem. Okay, we need to teach states of matter down in the lower grades, and I think it's pretty easy to understand that we have gases, liquids, and solids. There's actually a fourth state of matter, which typically don't teach at the lower grade levels, I guess, and it's plasma. That's what's in the sun. It's also in arcs. Like if you strike an arc in welding, plasma exists in it. And lightning, a lightning bolt, an arc of lightning coming down through the sky actually has plasma within it, the fourth state of matter. But for the most part, the expectations are you teach the states of matter as solid, liquid, and gas. And I think each of you have a pretty good understanding what those are. Okay, we want to teach the phase changes that occur with matter, or changes of state. We want to talk changes from solid to liquid, from liquid to solid, and so forth. So, like evaporation, okay? Evaporation, this diagram is wrong. Because this should be showing evaporation going that direction and condensation going this way. That's labeled wrong. Okay, I'll change that out. Okay, when you look at this PowerPoint on your on your own, you'll see I've changed this. Evaporation goes this way, okay? I pulled this diagram offline. I never paid attention. They aren't labeled right, either one of them. Okay, evaporation goes from the liquid to vapor, okay? Condensation goes from the vapor back to liquid. Okay, condensation occurs on your car on a cool morning when you get the dew on your windshield. Condensation occurs when you see the vapor trail of a jet going through the sky. That's condensation. Condensation also occurs in a bathroom when you take a hot shower and it ends up on the mirror and on the glass of the shower. Okay, that's condensation. Evaporation is where the liquid's going into the sky, going into the air. Okay, melting is when you go from solid to liquid. Freezing is when you go from liquid to solid. Okay, those are key terms for elementary kids to learn. And then sublimation is really the toughest for them to learn. That's where you go directly from a solid to a gas. Snow does it, okay, because snow doesn't have to melt to disappear. Okay, it sublimates too. Okay, most time it melts as the temperature goes up, but it also sublimates because they can stay cold outside and the snow never melt, but still go away because it sublimates. Okay, dry ice is another cool one for stage effects. Also put dry ice in coolers if you go on a good fishing trip. Okay, but sublimation is changing directly from a solid to a gas. Okay, heat. Okay, heat is a measure of energy that's been absorbed or transferred from one thing to another. Okay, it is just a measure of energy. Okay, it is a measure of energy inside something, and it's relative. All items, this, me, all has heat energy in it. This, the battery in it, at times you can feel that it's warm. Okay, it contains heat energy. All living things have a heat energy in it. So we want to talk about heat, what it is, and how heat transfers and moves around through things because it's always in motion. Okay, and that's what makes things happen. Okay, so we have two simple processes with heat. We're either heating things up or cooling things down. So we say heating and cooling, and that's a big area we have today. HVAC, people that work in that industry. But the process of increasing the internal energy of something, whether it's coffee or whether it's something you're cooking or whatever, is heating. The process of decreasing the internal energy is cooling. Okay. So now then, with this, the important things to get kids to understand is heating and cooling involves moving heat energy, transferring heat energy as a process. Okay, so heat transfer always naturally just takes place one direction, from hot to cold, from a warmer object to a cooler object. Now it can be objects, but it also can be across the air, okay, or across the sky, because the heating and cooling of the atmosphere is what drives our weather systems. How the weather moves from California to us is heating and cooling of the air. You want to teach that to the kids. In our houses, we have differential heating and cooling. Like in the summer, we're wanting to cool our house, so we want to trap that air in the house and cool it. Okay, so it doesn't transfer outside, the heat outside get in. So we put insulation in our houses. Okay, in winter, it's the opposite. We want to warm the house and keep the warm air in, keep the cold air out. And you talk to the insulation in the house helps make that happen. That's good stuff to teach kids. Okay. We measure heat energy with certain units. The units that we measure with are joules, calories, and BTUs. Okay, joule is actually a unit that's used to measure all kinds of energy. So a joule is like we worked with work, Newton meters in the previous unit. Okay, well, you still use it for measuring heat energy. You can talk joules and you can actually talk kilojoules of energy. Okay, that are heat. Okay, then you have calories, and just like we have nutritional calories, that's where those terms come from. It's actually a unit of heat energy. Okay, And what a calorie is, it is the temperature that it takes to raise, or I'm sorry, it's the heat that it takes to raise the temperature of 1 gram of water 1 degree Celsius. Okay, so that's 1 calorie. 1 calorie is also 4.18 joules. Okay, and all I want you to know now is what it is. We're not going to get into math of these because this gets thermal, like I said, thermodynamics, thermochemistry, and I think math gets beyond what you want to work with in elementary. But the key thing is know what they are, because you'll see, like on food products and so forth, it has so many calories in it. Okay, and that's what you're taking in your body. Okay, and when you're burning calories, okay, these are units. Okay, they are units of heat energy. Okay, and so when you're running, when you're jogging, and so forth, burning the calories, that's what we're talking. Okay, then when in heating and cooling, you can talk BTUs. BTU is British thermal unit, but that's not important for what we're doing. Just knowing that it is a heat energy unit, and it is the temperature it takes to. I keep saying that kind of backwards. It is the heat energy required to raise the temperature of 1 pound of water 1 degree Fahrenheit. Okay, on BTU you're talking Fahrenheit, whereas calories you're talking Celsius temperature. Okay, but they are heat energy units. These BTUs, like if you buy a new furnace, it's going to be so many BTUs. If you buy a new gas fireplace for heating, it's going to be sold in BTUs. Your stove, ovens, BTUs. You're talking heat units. The amount of heat, the higher the BTUs, the more heat and more hot they're going to get. Okay, those outdoor heaters you can put on your deck, they're going to be sold in BTUs. Okay, and that's what you want to teach students. Okay, then the last terms on this unit, this chapter is where we talk heat flow. There's principal ways in which, or key ways in which heat flows. You have radiation, convection, and conduction. Okay, and here we have this pot over this fire, and we're heating this pot of water or kettle of water or whatever you want to call it, pan of water. We're heating it up and we're watching what goes on. Okay, these currents in here in the liquid we call convection currents. That's convection heating. It can take place in liquids, it can take place in the air. Like in this room right now, this air is moving around as it's differentially cooled with air conditioning on. Okay, you have convection currents in the air. That's where you have registers in your house for the heat to come in, and then you have vents for the air to go out and keep the cycle going. Okay, that's convection. Okay, and that is movement of heat energy. Okay, so you have it in liquid, you have it in the air, you have it in gases. Conduction, on the other hand, is like this handle right here is made out of metal. Heat flows through it as it heats up. So where this hand is right now, it's going to get hot eventually. They're going to drop them and burn themselves or whatever. And that's why people get burnt with items. If you take a metal rod and throw it down in a fire, just one end of it, and come back later to grab a hold of it, the other end is going to be hot too because conduction took place. Okay, conduction, movement of heat energy through typically a metal. Okay, it don't always have to be metals, but it's most commonly metals. Radiation, on the other hand, is like you got the fire burning here, and the air is all around that fire. And if you can feel the heat energy coming out through the air, that's radiation. If this cup right here was hot, and I put my hand here and I can feel it's hot right here, I feel it out here, hot, 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 and then stops feeling so hot. But this is radiation. Okay, the heat radiating off, moving through the air, moving through space from the hot object. That's radiation. Okay, and that's it for this chapter. Have a good evening. Hope you learned something. Hope these are things that you feel comfortable teaching elementary students. Have a good one.